Welcome to statics. In statics, you will learn how to analyze forces acting on and within different structures. Here are three examples of a truss, frame, and machine that are central topics of analysis in statics. I want to point your attention that all the structures have a wide variety of shapes and sizes. In particular, if I want to focus my attention on trusses, you could see that in engineering practice, there are many ways to design trusses, and each design has its purpose, and this table certainly does not exhaust the wide variety of trusses one can encounter in practice. Here I would like to make a very important point. Understanding geometry in general is critical to understanding statics, and therefore I would like to remind you a little bit about geometry. Let me state that geometry is about 2,300 years old, and classical geometry was discovered in the book called Elements by Euclides, and pretty much the content of this book is taught in high school geometry classes. The geometry of Euclid was not very simple for calculations, and significantly later René Descartes introduced analytic geometry. Analytic geometry has two basic ingredients. Descartes brought to classical geometry, trigonometry, and Cartesian coordinates. Let me remind you that in analytic geometry, a point P is identified by its Cartesian coordinates x and y, or polar coordinates r and theta, and the relationships among these coordinates are well known and showed here. So we either can express Cartesian coordinates x and y in terms of the polar, or polar in terms of the Cartesian. Also, analytic geometry is helpful for computing distances between points. So here I consider points P and Q, and in Cartesian coordinates, the distance between P and Q is given by the following expression. Note that, of course, the distance from P to Q is the same as the distance from Q to P. We're interested in solving triangles, and this will be done using the law of cosines, the law of sines, and the basic relationship for computing the area. Let me bring to your attention that the law of cosine, as written here, involves known A, B, and the angle gamma. And our task is to compute C. We could have written similar equations for the sides A and B. So in general, we can write three different laws of cosines. The same way for the area, we can take any base and any height, and so we can calculate it in three different ways using three different bases and three corresponding heights. Two triangles are similar if their sides, corresponding sides, have the same ratio, or if their angles are equal. There are other ways to define similar triangles, but these are sufficient for our purposes. So let me use this basic knowledge to solve several representative problems. The first problem involves a line DE that is parallel to the base AB, and our task is to prove that the triangles ABC and the triangles DEC are similar. To this end, I will denote the angles at A and B by alpha and beta respectively. And now I observe that the lines DE and AB are parallel, and therefore the angle at D must be equal to the angle at A, and therefore the angle CDE is equal to alpha. I can use exactly the same argument to demonstrate that the angle DEC is equal to beta. Now if I look at the triangles ABC and DEC, I observe that these triangles have the same angles because the angle at C is shared by the triangles, and of course the other angles are equal to alpha and beta. In the second warm-up problem, I look at two similar triangles, and I am given that the ratio of their sides is equal to R, and my task is to calculate the ratio of the areas. To do this, I will simply write down the area of each triangle and rearrange this ratio such that I have ratios of the sides, A prime, B prime, and the ratio of the sides. But since the triangles are similar, then gamma and gamma prime are equal to each other, and therefore the resulting ratio is equal to R squared. In this problem, we're given a triangle ABC, which is partitioned by the line DE into two equal parts. It means that the area of the triangle DEC is equal to the area of the trapezoid ABED. Alternatively, we can say that the area of the triangle DEC is half the area of the triangle ABC. We're given the lengths C and the angles alpha and beta. Let me remind you that the distance between two parallel lines, in our case AB and DE, is a segment perpendicular to both lines. To this end, I will draw a line CFG. The points F and G are the intersections of that line with the lines DE and AB, and the line CFG is perpendicular to both DE and AB. So my task now is to compute the lengths FG. I will begin by looking at the two similar triangles ABC and DEC. Since the ratio of their areas is equal to 2, the ratio of the bases is equal to the square root of 2. Also, I can claim that since the ratio of areas is 2 and the ratio of the bases is square root of 2, the ratio of the heights also should be square root of 2. Next, I will compute the height CG using the triangle AGC, and from this triangle I conclude that the height is equal to B sine alpha. And to calculate B, I will look at the triangle ABC and use the law of sines to replace B with C and the angles. Please verify that this expression is correct. Now I can compute the lengths CF from CG and this ratio. And finally, I can calculate the length GF as the difference between the lengths CG and CF, which gives me the answer shown. In this problem, we have a triangle ABC inscribed in a circle. The base AB is a diameter. The chord BC forms an angle alpha with the diameter. The radius of the circle is equal to r, and our task is to find the area of ABC in terms of alpha and r. Let me begin by looking at the triangle OBC, which is isosceles because both OB and OC are equal to r, and therefore the angle OBC and the angle OCB are equal, and the angle OCB is of course equal to alpha. Now I can compute the area of the triangle OBC using the formula 1/2 r squared sine p minus 2 alpha, because the angle at O is equal to p minus 2 alpha. I can also compute the area of the triangle AOC because I know the edge AO and the edge OC are equal to R, and the angle between these edges is equal to 2 alpha. And as a result, I obtain that the area of the triangle ABC is equal to the sum of the areas of the triangle OBC and AOC, and it's equal to r squared sine 2 alpha. I recommend you to establish that the angle ACB is the right angle no matter what the angle alpha is. This is a relatively hard problem. It involves an isosceles triangle ABC with AB equal to BC. The triangle is parametrized by the angle alpha. The triangle is inscribed in a circle, and the point D is chosen such that it divides the chord BC into 2 equal parts. Our task is to find the angle theta, which is formed upon intersection of the extensions of the lines BD and AC at the point E. To solve this problem, we begin with identifying the center at O and constructing the following lines. The line going through O and B bisects the triangle ABC. The lines OD and DC are the radii that connect the center to these points, D and C. Now I will go through a sequence of isosceles triangles. The first one is ABC. Since the line BO bisects the triangle, the angle beta is equal to 90 degrees minus alpha. Similarly, the other angle at B is also equal to beta. Now I will look at the triangle OBC, which is isosceles because OB and OC are 2 radii, and in this triangle the angle at C is equal to beta, and then I can calculate the angles at O, and both of them are equal to alpha. Now let me look at the triangle OBD. This is an isosceles triangle, and therefore the angle at D is equal to 90 degrees minus alpha over 2. Now if I look at the angle ODE, it is complementary to the angle 90 minus alpha over 2, and therefore it's equal to 90 plus alpha over 2. Now let me come back to the triangle ABC and observe that the angle at C is equal to alpha, and therefore the angle BCE is equal to 180 minus alpha. Now I will look at the quadrilateral ODEC. In this quadrilateral, I know the angles at D, O, and C, and therefore I can compute the angle at E, and the expression is as follows: 360 degrees. The total number of degrees is contained in the angles, right? And then I subtract the angle at D, the angle at O, and the angle at C, and the answer is alpha over 2. The next problem is a design problem, and in this case I'm interested in building a truss. A truss is formed by two semicircular bars connected by straight blue bars. The blue bars are located along 45, 90, 135, and 80 degree directions. But what you will learn in statics, that such structure is not optimal. If I want to have a good load-bearing structure, I better replace these rectangular cells with triangular cells, and therefore I will put the reinforcement bars, which I show by green line. So my task is very simple. I know the weight per unit length of the bars, and it's the same cross section, and so the bars have the same weight, and my task is to determine the weight of the entire truss, provided that the inner and outer radii are given by A and B respectively. To solve this problem, let me introduce Cartesian coordinates so that their origin is at the center of the semicircles, and I will also denote the supporting bars AB and CD. Let me start by observing that the weight of the red bars, which are the semicircles, is simply equal to their weight per unit length times their length, which is Q times P A plus B. For the blue bars, the weight again is equal to Q times their length, and they have 5 blue bars, and the length of each bar is B minus A. Now, in order to find the length of the reinforcement or the green bars, I will start with the bar AB, and I observe that the points A and B have the following X and Y coordinates. From these coordinates, I can compute the length of the bar AB, XB minus XA squared plus YB minus YA squared, which gives me this compact expression. I can do exactly the same thing for the bar CD, where I define the coordinates of XC, XD, YC, YD, and compute the lengths. This allows me to calculate the weight of the green bars. I want to pay your attention that I'm using a factor of 2 here. This simply reflects that the length of this bar is equal to the length of CD, and the length of this bar is equal to the length AB. And once I obtain the expression for the green bars, I can calculate the total weight by summing the weight of all the bars, and that's the equation. So this concludes my presentation. What I ask you to do is to find a suitable geometry book, maybe the one you used in high school or maybe some other book, and get yourself prepared for the course. Geometry will be an integral part of statics. Thank you very much and have a wonderful day.